Hi, I'm Su-Xing from KIST. Please let me briefly present our latest research on multiple dynamic outlier detection from a data stream by exploiting duality of data and queries. So, what is an outlier? Outlier can have many different definitions, but most intuitively, outliers are the most different data points compared with other data points. So in this two-dimensional space, those two data points have very different attribute values compared with those of other values, so that we can easily think that those two data points are outliers. So continuous outlier detection from a data stream is to find outliers from the data points continuously coming from multiple sources. So it has to be fast, accurate, and it can be applied in many applications such as fraudulent transaction detection in finance and abnormal heartbeat detection in healthcare and faulty detection in manufacturing systems. In outlier detection from data stream, there is a multiplicity dynamicity challenge. As data points are continuously coming from multiple sources, there must be some changes in data distributions. So the outliers can be multiple and their characteristics are changing over time. As you can see in this figure, at every time step, the distribution of data points are changing, and at the same time, the dose of outliers are also changing. The number of outliers are changing, and their characteristics, which means the degree of similarity compared with other data points, are also changing over time. So we have to find those multiple outliers at each time step, and also their changing characteristics should be captured by outlier detection algorithms. So in real life, we can find many applications which show multiplicity dynamicity challenges. For example, in financial corporate, they want to find some credit card fraud or financial fraud so that they can protect their customers and their resources. For example, fraud monitoring query can be defined as the similarity threshold, report cycle, and time scope, which means that from credit card transaction streams, some transactions may have very dissimilar characteristics compared with others, and the analysts want to find those abnormal transactions at every time step, and also they want to consider the most recent transactions in a certain time period. So some analysts want to find rare transactions of short duration, such as in every 5 minutes, report the transactions whose similarity is less than 1% of the average similarity of other transactions, considering the last 1 hour. And the other analyst may want to find extremely rare transactions of long durations, such as in every hour, similarity should be less than 0.1%, and the considering duration of time is the last day. As you can see in this example, there can be many analysts which have different types of fraud monitoring query. So in many real-world applications, and in this credit card fraud detection, many internal or external factors affect those applications, show multiplicity dynamicity challenge. For example, in this card transaction trend, the external factors such as pandemic lockdown or tax law revision may affect the different types of outlier detection query. And internal factors such as income change or cardholder characteristics change, or the new fraud techniques may make analysts give different types of queries. So this multiplicity dynamicity challenge on outlier detection from data stream should be coupled with a very novel outlier detection method. So more formally, we define the multiplicity of continuous outlier detection query and dynamicity of continuous outlier detection query. So as I explained in the previous example, various analytic purposes leads to concurrent learning of multiple queries. And evolving context or characteristics of our outliers lead to non-stationary queries over time. So in this figure, there is a dynamicity and multiplicity challenges in outlier detection from data stream. So we have multiple users who want to find outliers from a data stream, and they add or remove their own outlier detection queries at each timestamp. So it's called dynamicity of those challenges. And at outlier detection system, there are many concurrent queries running on this system. So we can see this as a multiplicity challenge, and real-time alert detection algorithms should consider those multiple queries at each timestamp and detect outliers from data streams from different sources. And it should be accurate and it should be fast to support real-time applications. So before talking about our method on outlier detection from a data stream, I want to introduce the most popular and powerful definition of outliers. So distance-based outlier is defined as a data point with very few neighbors within a certain distance. So distance-based outlier detection in data stream, which is just called DODDS problem, has 4 parameters to detect outliers from data stream. Given a window size, a slide size, a neighbor count threshold, and distance threshold, a data point in a data stream is an outlier if it has less than k data points within a distance R defined by the sliding window with size W slided by S. If not, it's an inlier. So in this two-dimensional data stream, we have a slide size, window size, and neighbor count threshold, and distance threshold. With these parameters, in every sliding window, the algorithm must find distance-based outliers. So in the first window, we have 6 data points, the most recent data points in this data stream. And data point 6 is an outlier defined by the distance threshold and the number of neighbors count threshold. And in the second window, there is no outliers found. And in third window, the data point 8 can be defined as distance-based outlier. So DODDS problem has to find those distance-based outliers in every sliding window. So in this research, we introduced multiple dynamic version of DODDS, which is called MD-DODDS problem. So given a set of outlier detection queries, and each of which is defined by different values on each parameters, and find all outliers detected by each query in this query set, which changes over time. So in a data stream, one-dimensional data stream, for example, users may add or remove to or from a query set. And in this query set, there are many different queries, and each query defines different types of outliers by their own parameters. So for every timestamp, outlier detection method which solve multiple dynamic DODDS problem, they have to process different queries and considering their different parameters and decide whether a certain data point is an outlier or not. So there are some related work to solve this problem, but existing algorithms' ability to handle the multiplicity and dynamicity challenges, and none of them can fully handle those two challenges. and some of them may not solve those two challenges, and some of them may only tackle the multiplicity challenge. So DODDS algorithms, which only consider a single outlier detection query, they have their own optimization techniques to process outlier detection query accurately and fast, but they cannot deal with multiple or dynamically changing outlier detection queries. And in MDDODS problems, there are some algorithms to process multiple outlier detection queries at the same time, but they did not consider the case where the outlier detection queries are changing over time. So let me introduce the main idea of the proposed algorithm. So given these dynamic and multiple outlier detection queries, the existing algorithms conducted separate processing, which means that at each timestamp, we have multiple outlier detection queries, and those query set changes over time. And each timestamp, each query process each data point and decide if this data point is outlier or not by this query. So the existing algorithms should process multiple computations for each data point, query pairs. And at the second timestamp, as queries are changing and the data distribution are changing, and each data query pairs should be processed redundantly. But in our algorithm, we propose unified processing instead of separate processing. So in query side and data point side, we can group the similar queries and we can group similar data points. And we also group the data and query pairs as a unified group and only process the minimum but sufficient computations in each group and use those computations to answer each query data pairs answers. And at the same time, as time goes, the query set is changing and data points are also changing. So we update only the minimum information for each unified group, which is called net change of unified group. And we update only the minimum number of minimum informations for answer each query data pairs. So this main idea is called duality-based unified processing. So there is a duality in grouping similar queries and similar data points and process the data query pairs in a unified way. So this group-wide processing, exploiting both data and query similarities over time, can have huge benefits on the detecting outliers from data stream, especially when there is a multiple outlier detection queries and those are changing dynamically. We can save huge computation time and also huge memory consumption. So there are two main techniques for duality-based unified processing idea. The first one is grouping of data query pairs, which is called CBRQ, constrained Boolean range query. So given a data point and a query, a CBRQ can be defined and it returns true if a data point meets requirement of query and false if not. So given 3 queries and 5 data points, each query can be projected into data space for each data point. So we have 15 CBRQs for each data query pairs. And we can group these CBRQs either considering data similarity or query similarity. But ultimately, we can group those CBRQs both considering data similarity and query similarity. And we can get 2 unified groups, which means that if we compute the minimum but sufficient computations for each unified group, we can get all the result in the CBRQs inside each group. And the second technique is prioritized group processing. So each unified group, we make some prioritization for each CBRQ, and we first process the most important GVRQ and propagate their result to others. This can be possible because of some restrictive relationship between GVRQs. For example, Q1 is more restrictive than Q2, considering some their requirement relationship, and the result of Q1 for the data point xj can be propagated to the result of Q2 for the same data point. So by answering the minimum number of and the most important query first, we can propagate the result to other query data pairs. So using those two techniques, by employing the main idea, we introduce the MDR algorithm. So MDR algorithm conducts three main phases in every sliding window. In first phase, the unified groups are updated. So in the previous timestamp and the current timestamp, the MDR algorithm updates the unified group mapping, which contains the information about unified groups, and we only update the minimal number of net changes information between the previous unified groups and the current unified groups. And using these unified groups, MDR first closely processing those unified groups and return the answers for each group of GVRQs, and it can return false or true for each subgroup of GVRQs, and those answers can also be propagated to others considering the restrictive relationship. And in the third phase, the MDR algorithm processes the unanswered GVRQs in a finite manner. So the unified groups are also reduced, and this reduced search space, and each GVRQ are processed to get the answer false or true. And also in this finite processing procedure, the GVRQ answer can be propagated to the others, considering the restrictive relationship. And finally, GVRQs returning true and their pairs are reported so that the users can know which data point are returned as outliers by which queries. And those three phases are conducted in every sliding window to get the distance-based outliers defined by different queries. So we evaluated our algorithm in different real-world data sets, and their dimensionality varies from 1 to 55, and their size are around 1 million or less. And most importantly, to simulate the multiplicity and dynamicity challenge, we made some different types of parameters to generate query set. So number of queries can vary from 1 to 1000, and the condition, which is the query parameters, can change. And the condition value distribution, such as the, for example, the number of neighbors threshold, the values can vary over different queries, and they follow some different types of distributions. And the change rate of query set also varies from 0%, which does not change, and 1%, which change entirely. So the overall performance comparison shows that compared with the two state-of-the-art algorithms, our algorithm achieves less processing time and less memory consumption and processing multiple and dynamic outlier detection queries. And also in different types of distribution of core condition values, our algorithm achieves the less memory and less processing time for these different types of experiment settings with different distributions. So, which shows that in real world, our algorithm can be robustly perform other state-of-the-art algorithms processing multiple dynamic outlet detection queries. So there are a bunch of other interesting experiment results. Please check out our paper for more details. So let me conclude this presentation. The processing multiple and dynamic outlet detection queries are very important problem and can be applied in many applications. But existing algorithms separately process our data query pairs and cause redundant computations. So we proposed Duality-based unified processing enabled by data query process grouping and prioritized group processing techniques. So we could achieve less computation time and also less memory consumption to process multiple and dynamic outlet detection queries. So thank you for listening, and please check out our paper for more details. Thank you very much.